Okay, let's move on to this problem here. We're given here a coil. We're told that it has 100 turns, has a diameter of 7 centimeters, and we're told that it's made of 0.5 millimeter diameter copper wire. So we know everything there is about the coil. There is a magnetic field that's perpendicular to the coil. At what rate must that field increase if we want to induce a 4 amp current in the coil? So it's quite a bit of current. So I've drawn a little bit of a diagram over here to the right, just reminding us that we have this really nice normal relationship here. So we're looking at the coil from the side, right? And the coil itself is normal to B. B is, if you look at the notation, going into the page here and is uniform. So we'll start with Faraday's law, which reminds us that if we want an EMF, that EMF is equal to d phi dt. And we remember what the negative sign is really about there. That's the Lenz's law contribution, right? That just reminds us that the induced current is always going to create a B field to counter the change. That's what that's about. And flux, let's just be reminded of what flux, the magnetic flux looks like here. That is B dot dA. So the amount of field that is permeating through some defined area. So for this particular problem, we have B is normal to dA everywhere, right? For this whole entire setup. So that's really nice. What that allows us to do is say, all right, what that tells me is that this integral of B dot dA, since they're everywhere normal to one another, is just simply the product B times the total area A. Okay, so let's figure this out then. The EMF, what's that going to be equal to, is going to be equal to negative d dt, then the quantity of flux. But remember that we have 100 turns here, right? So this ends up being, instead of just B times A, N times B times A. Every single turn contributes there. The turns are really powerful, remember. So, and I'm going to go ahead and drop the sign because we don't care about direction here. That's not what's important. What's important is the amount of current that we induce in the coil. So I'm going to go ahead and write this more simply as N. Well, I'll just write it this way, d dt N B A. Okay, now the area is not changing. The N number of turns aren't changing. So this means that we can simplify how we write this out. The N comes out front, it's a constant. The A comes out front, it's a constant. This is a constant diameter, right? And then that gets multiplied by dB dt. There we go. Now we're getting somewhere. And the area I can write as pi r squared for this particular coil here because it's a circular coil. So we can write it in terms of that. So I can write that as N times pi r squared times dB dt. Okay, and it's dB dt that I'm solving for. Notice the problem is asking me for at what rate does the B field have to change, right? Cool. And since I'm talking about current here, and Faraday's law just talks about EMF, I need to bring forward another equation to relate those two, and that will be E equals I R, right? And this is where the copper itself comes in, the fact that we care about the diameter of the wire. If you're wondering why would we care about that for this case, it's because that is going to let us know what the resistance is in that wire. Remember, this is still a circuit, right? This is still a circuit. Faraday's law only gives us the EMF. In order to figure out the current, that's going to depend on the resistance of that particular circuit. So in order to solve for the resistance of copper, or of this particular wire, we need resistivity of copper times the length of the wire divided by, now this is the area of the wire itself. So I'm going to just use an A prime or something right there for that particular cross-sectional area of the wire. If you pop all those values in, and you can see that in the written solutions, what you will get for resistance is something around 1.9 ohms. So we have our resistance value there. So what I can say is, using this equation here, right, my left-hand side is going to be N times pi r squared dB dt is equal to IR. Great. And they gave us the 4 amps for the current. We just figured out the resistance, right? So we have everything we need in order to solve for this. So I can now solve for dB dt. That gives me IR divided by N pi r squared. My current is 4 amps, resistance 1.9 ohms. There are 100 turns in this thing. Pi is pi. And we're told that the coil is 7 centimeters in diameter. So that means the radius is going to be 3.5 times 10 to the negative 2 meters. We need SI here, and that needs to be squared. Cool. So if I calculate this whole enchilada out here, I'll get something like 19.75 Teslas per second. And remember, it's the change in B field over time that's being asked for here.